Chapter 5 will deal with thermochemistry. Thermochemistry is a subsection of thermodynamics, which is the study of energy and its transformations. We'll get more into thermodynamics later on in the year. But in our study of thermochemistry, we'll talk a little bit about the nature of energy. We'll talk about the first law of thermodynamics, enthalpy. Enthalpy is a reaction, calorimetry, which is how we measure the heat flow, Hess's law, enthalpy is a formation, and finally food and fuels. Obviously, energy is a very important part of our everyday life. Not a whole lot can happen without the transfer of energy from one form to another. Energy is the ability to do work or transfer heat. Work, when we use energy to do work, we cause an object to change its motion. An object that has mass to move or to stop or to change its direction. In terms of heat, energy is used to cause the temperature of an object to rise. The two general categories of energy are potential and kinetic. The potential energy is based on the position of the object. So in terms of the bike rider here, the potential energy is equal to the mass of the rider times the height that he is above the potential of the bottom part of where he could go from top to bottom times the acceleration of gravity. In terms of charged particles, the potential is based on the difference in charge between the two particles that are either attracting or repelling. So the electric potential energy is equal to a constant, K, times the charge on the first object, charge on the second object, divided by the distance between them. K, constant, has a value of 8.99 times 10 to the 9th joule meters per coulomb squared. Remember that the constant is used so that the units will cancel out. The charge on an electron, if you recall from before, has a value of 1.60 times 10 to the negative 19th coulombs. So you can see that in the formula, the charges would cancel out, or the coulombs would cancel out, the distance would cancel out, and you'd be left with the electric potential in units of joules. And we'll get to where the units came from in just a moment. Over on the right, we had the bicycle rider now going down the hill, so that potential energy is now being converted into kinetic energy. And we have our classic formula for kinetic energy equal to 1/2 the mass times the velocity of the object squared. There are three ways to derive the units for energy. First, in terms of the kinetic energy, we take 1/2 mv squared. If we take an object that has a mass of 2 kilograms that is moving at a velocity of 1 meter per second, when we combine all these units together, we get an energy of 1 joule. The other way we can look at it is if we take work, the amount of work done on an object is equal to the force acting on the object times the distance over which that force acts. So the standard unit of force is 1 Newton. Acting over 1 meter, will be 1 joule worth of work. The other common unit that we have for energy is the calorie. Calorie is defined from a heat standpoint, and that 1 calorie is the amount of energy it takes to raise 1 gram of water (1°C). So 1 calorie is equal to the energy it takes to raise 1 gram of water 1°C. To convert between the two, we have 1 calorie is equal to 4.18 joules. So this allows us to convert between our derived unit of joules and our practical unit of calories. In analyzing the energy that's exchanged, probably one of the most important things is to define 2 aspects, one being the system that we're dealing with, and the second being the surroundings. So in the picture here, we have a potential reaction between hydrogen and oxygen. So we would define the inside of the container, the hydrogen and oxygen molecules, as our system, and the container and everything outside of it as the surroundings. And we can define things in any way we want to, but that's going to make it most convenient in terms of identifying the energy exchange. Now, the system that we have set up here would be a closed system. Right? In a closed system, the energy can be transferred from the system to the surroundings or surroundings to the system, but no matter can be transferred. So all of the matter would stay within the system. So we can have heat flow into or out of the system. We can also have the system do work on the surroundings by having the piston move up. So in other words, the system would push the surroundings, it would do work on the surroundings. Or if we were to do the other way, if we were to push down on the piston, then the surroundings would do work on the system. So it's very, very important that we get those kind of ideas down. Work done by the system, piston would go up. Work done by the surroundings on the system, piston would go down.